Okay, so for the last 3 weeks here, we're going to be focusing on our last module or our last major topic, which is going to be trees and tree-based data structures. Today I'm going to get started by making some very basic definitions and giving a motivation for why we really like trees and tree-based data structures. Basically, the motivation has been building up to this point. Our motivation so far has been to introduce collection data structures. And what I mean by that is simply just data structures that hold things, right? Ultimately, you want to process data, so you want to be able to do three basic operations. You want to be able to insert data. You want to be able to retrieve data, because if you can't retrieve it, then there's no point in putting it into it. It's like throwing it away. And you want to be able to delete data, right? So these three basic operations, you want them all to be efficient. And now that we have a notion of what efficiency means, we can start looking at what we've seen so far and characterizing each one of these things. For example, array-based lists. Array-based lists. So what did we observe there, right? What's efficient there? Well, you can go ahead and get things at the ith element really efficiently, right? Because it has an array backing it, so it has random access. So you've an index-based retrieve method is order 1, right? Because it just requires you to compute a memory offset and then jump to that memory offset. What about an arbitrary insert or remove, though? Right? An arbitrary insert or remove. And what I mean by that is, what if you wanted to insert something? There are 100 elements in there, and you want to insert something at index 10. What are you going to have to do to make room for it? You're going to have to shift all this stuff down, right? And so potentially, both of these things are going to be order n, where n is the number of elements already in the list. If I've got n elements there and I want to insert at the head of an array-based list, then I've got to shift n elements down and then to make room for that new element. Now, another way of looking at this is inserting at end, insert or delete at the end. That's going to be order 1. Or constant, because you can jump to the end immediately as long as you're keeping track of how many things are already in the list, right? Some of these things are very efficient, right? It doesn't get better than order 1, constant time. But on the other hand, some of these things are very inefficient. What's another thing that we can do to exploit an array-based list? What if it's already sorted? If sorted, then an arbitrary search, right? In other words, a retrieval is going to be using binary search. It's going to be order log n, right? But that requires there to be structure, right? And we don't have that structure necessarily with just a generic array-based list. We can go ahead and sort that, and that's what you're going to be doing this week's lab. You're going to be benchmarking a bunch of sorting algorithms that you've seen or that we looked at just recently, and you're going to be looking and seeing which ones are the best ones, right, in practice, okay? Then we went on and looked at another data structure, a linked list-based data structure. If I use a linked list, then some of the things that were inefficient become efficient. Some of the things that were efficient become inefficient. Some things stay the same. Right? So what are the highlights of a linked list? An insert at the front or end is going to be order 1. Right? Because all it takes is to create a new node and then link it to the other nodes. As long as you're keeping track of both the head and the tail element, right? And there's really no reason why you wouldn't do that in a real implementation. So inserting at the front, inserting at the end, make them ideal for queues and stacks, which we'll mention here in a second. But what about an arbitrary insert or an arbitrary, what about an index-based search now? index-based retrieval. What do you have to do now? If I've got 1,000,000 elements in my linked list, and I want the one right in the center, the thing at index 500,000, what do I have to do? I have to either start at one end or the other if you want to. You can start at the head and make a traversal all the way down, right? In other words, it's going to be order n, right? Another observation, what if it's sorted, right? What if it's a sorted linked list? Can we exploit binary search now? What does binary search do? Given an array, basically, it can jump to the middle and determine, is this the thing I'm looking for, or do I need to recurse on this end or this end? Right? The key there was you were able to jump to the middle. Are you able to jump to the middle of a linked list? Nope. There are things called skip lists you can kind of do that. It's kind of a hybrid between an array-based list and a linked list. But even then, you're not going to have a performance of order 1, right? And that's something that we didn't cover in this class, and for good reason, because they're way more complicated, right? So you can insert at the front, you can insert at the end, but an index-based retrieval is going to be order n. What if I have already the nodes that I want to insert in between, right? So in other words, I've already done the work to get to where I want to insert it. Now inserting it, is that going to be too much trouble? Create a new node, link this one to that one, link this one to the next one, and you've got now you've made your chain longer, right? But the key is that you had to get there first. So an index-based insert, that's also going to be order n, right? Index, basically anything where you have to do an index-based operation, insert or removal, is going to be order n, because you have to get there to begin with. But once you're there, then it's going to be an order 1 operation. Then we started looking at stacks and queues. All operations for stacks and queues, that is push and pop, and for queues, what was it again? What did we call those? NQ and DQ. That's what I like to call them. DQ are all going to be order 1. But why is that? It's because we're not allowing the arbitrary things that give you a linear performance here, right? We're saying that you can only push and pop. You can only NQ or DQ. In other words, you can only work from the ends of your linked list implementation, or your more generally your deck implementation, right? In other words, it achieves efficiency via restricting access, right? So it kind of cheats. Its basic operations are all going to be efficient, but you're only allowed to do certain things. You can't arbitrarily, jump to the middle of a stack and pull the dish out. Otherwise, the entire stack is going to fall, right? So our ideal would be that all 3 operations would be order 1, right? Now we're not going to get there. If you want that, you can get close to that using hash tables. Hash tables, hash maps, hash sets, anything that has based on a hash table can kind of give you what's called amortized order 1 operations, right? We're not going to cover hash tables, but you can certainly use them. You should be using them. I've encouraged using maps from day 1. If you want a set, use a hash set. If you just want a straight up hash table, then you can also use a hash table. Almost every single programming language is going to support some sort of hash table backed data structures, in which it's going to offer amortized order 1 operations. Now, what does amortized mean? It just means that over the long haul of the life of the data structure, the cost of your operations will flatline to look constant. That it's not actually constant, because sometimes to achieve this kind of performance, you have to rehash things. You have to build a new hash table, and that is quite expensive. And so it's only amortized, in other words, over the long haul. Right? It's kind of like loans. What's the amortized cost of this loan? because each month you're paying interest, but you're paying it down as well, right? Your balance starts up here that you've taken out a loan on, and then each month it goes down a little bit, but your payment is fixed, right? As you go, as you get longer and longer in the loan, you're paying more and more to the principal, and so it's costing you less and less each month. But the amortized cost is looking at the cost over the long haul of your 30-year mortgage or something like that. And that's where we get that name, amortized cost. So if you average out everything in a hash table, it all looks constant, right? We're not going to get there exactly, but we are going to start looking at another data structure, trees that have the potential for order, log n, insert, retrieve, and I'm going to emphasize potential here, and delete operations. All right? So we're going to get we're going to make more progress towards that ultimate holy grail hash tables, but we're not going to make ultimate progress. But remember, when we talked about sorting and we talked about n log n, we called that quasi-linear. What might you call this? Just a log n. It's quasi-constant. For all intents and purposes, even for very large data sets, this is going to be very, very, very slow growing. Right? Again, put it in perspective. If you've got a trillion elements, or if you've got a quadrillion elements, right? Or however big you want it, right? If you've got 10 to the 12 elements, taking a logarithm of this means that it gives you about 12 log base 2 of 10. That's going to be less than 3 or so, 3 point something. So it's going to be less than or equal to 40, right? 40 comparisons to do an insert, 40 comparisons to do a retrieval, 40 comparisons to do a delete. If you've got a nicely built tree, right? And so all that's really important is this exponent up here. How many elements do you actually have? I have billions or trillions or quadrillions. Well, that's okay because you're still only going to be doing 40 comparisons to do all of these operations, right? Just like binary search. Put binary search into perspective, right? And you see the huge potential savings over even linear algorithms. Okay? But before we get there, we need to define what a tree is, right? So, definition. And to start, I'm going to define a general graph, right? And there's a technical math definition, but I'm going to give you the high-level abstract dictionary definition. So, a graph is a collection of connected nodes. Here, let me rephrase that. Of nodes. Sometimes these are called vertices. We like to call them nodes over here in CS2 because ultimately they're going to be holding data, and vertices may or may not be holding data. Nodes definitely hold data. Kind of like nodes from a linked list, right? This node is connected to that node, is connected to that node, and also the nodes hold data, whatever you're storing in your collection. So a graph is a collection of nodes, vertices, connected by edges. Right? And our edges will be undirected for this course, right? These are going to be undirected edges. Right? Generally, nodes will contain data, like real data, invoices, products, right? And whatever you want to put into your trees, into your nodes, like we did with linked lists. For the purposes of presentation, though, I'm going to restrict myself to integers and letters, just to give them labels, right? Or labels, right? Again, edges will generally only deal with undirected edges, right? So let me go ahead. This is a graph so far. We haven't talked about trees yet. Let me just go ahead and draw you a picture here. It's just a very simple graph. I'll keep it A, B, C, and D. Right? Here there are four vertices or nodes, right? And I can connect them pairwise by drawing edges, right? And I'll draw this edge, this edge, this edge, this edge, and I don't know. I'll go to A goes to D. I'll go ahead and draw it like this. All right? How many edges did I end up drawing? 1, 2, 3, 4, 5. There are 5 edges in this example. Right? The nodes have labels A, B, C, D. Right? What else can you say about this graph? Right? Well, the nodes, 4 nodes, 5 edges. Each edge connects a pair of nodes. Okay, so this is just a generic general graph, right? There's a little bit of structure here. If you notice, I drew it such that I drew all the edges so that none of the edges are crossing. That's called a planar graph because you can draw it in a plane. There are things here called. There are several things here called cycles. For example, if I start at C, and I go up to B, and I go over to D, and I go back to C, right? This is a cycle, right? Because you can go in a circle or circuit. Is there any other cycle here? A to B to D over to A, right? So there's another cycle. You could go A to B to C to D, then over to A. That's another cycle. So in this particular example, there are many cycles. Right? Let's take a look at this cycle again. C to B to D, and then back to C. What's another cycle from another perspective using the same vertices? Going from C to D to B to back to C. Right? So there's no orientation because there's no direction, right? You could say that A comes before B, comes before C or something, but that's just because you're used to English and you're used to the alphabet. Whatever data is being held in there, those are just random labels that I chose. So this is a very general graph. Graphs are great because they can model a lot of different things. Most generally, a graph is a relation, and you might be covering relations right now in 235. Relations are the basis of relational database management systems, right? That if I've got an edge here, A is related to D, and B is related to C, C is related to B, right? It's symmetric. This one's not transitive, but that's okay. There are lots of different properties that you can come in and bring in and talk about general graphs and general relations that then have implications for other data structures and other areas of computer science, like relational database management systems. Right? What I want to do, though, is use these for a different purpose. I want to create a graph that is more structured. Right? And the way that I'm going to do that is by removing all those cycles that we just observed. Definition. Right? A tree is an acyclic graph. Right? In other words, a graph with no cycles. Right? So, was this thing I drew here, is that a tree? No, because it has several cycles. We identified all those. Right? One way that you could do that, here's an example. A to B to C. Now, can I go from C to back to A? That would immediately form a cycle. But I can branch out, right? D, E, F, G, right? I can look at another example here, A, B, C, and then I can branch off of that if I really wanted to with a bunch more. And at this point, I'm not even going to bother labeling them anymore. There's a bunch of vertices hanging off of these things, right? It doesn't have to be organized. It doesn't even have to go in any particular order. I've got A, B, C, D, E, F, G, H, I, J, and say K, and then draw circles on all of these things to denote that they are, in fact, nodes, right? Don't read anything into the labels, right? This is a tree. This is a tree. If I consider both of these things together, what happens when you have 2 trees, 3 trees, 4 trees? Eventually, you get into what's called a forest, exactly. And so two trees doesn't necessarily make a forest in real life, but as far as computer science goes, two trees is enough to call it a forest. We're not going to talk about forests. Instead, our trees are going to be connected, right? Our trees are always connected, right? So we will not consider forests. All right? Well, that's pretty good. There are no cycles, so what are some of the implications of that? Right? If there's no cycle, then that means that we're kind of giving it more restriction. We're giving it more structure. Okay. So if there's no if there's no cycles, then immediately a few things occur to me. Right. Let me go ahead and restrict my attention to this first one. Let's do that same example that we did before. Count up the number of nodes here. How many are there? 1, 2, 3, 4, 5, 6, 7. Right. There are 7 nodes. Now, how many edges are there? 1, 2, 3, 4, 5, 6. All right? 6 edges. Now, let's look at this one. How many nodes were there? 9, 10, 11. Right? How many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So 10 edges, 11 nodes. Do you see a pattern? What's your first observation? If I've got n nodes, so a tree with n nodes will have how many edges? N minus 1, right? Wow, that's really highly structured already, right? Not by restricting my attention to things with no edges, then I've got a guarantee here that if and of course that it's connected. If I've got n nodes, then I know exactly how many edges I have, right? Not only that, but another observation between any two vertices, or nodes, there will be exactly how many paths from, let me go ahead and give those names, let's say U and V, from U to V. Right? How many paths are there going to be? Again, let me go and look at this example. If I want to go from A over to G, how do I get there? I can go from A to B to C to D to G. Okay, that's a path, right? If I travel through this graph, then I can go from here to here to here to here, right? Just go from one node to the next node as long as it's connected. Now, it's not going to be possible to go from A to E directly here because they're not connected. But of course, I could go from A to B to C and then over to E. That's a path. So there's one path here, at least, between one node and to another node. How many other paths are there how many other ways are there of getting from A to G? I could go from, you might be thinking A to B to C, then over to E, then back to C, then over to D, and over to G. Well, why would you take that? Why would you take that route, that dead end route, and then have to backtrack? We're also only ever talking about simple paths, paths that don't traverse the same vertex or the same node or the same edge more than once. Okay? So if I go from A to B to C to D to G, is there any other way that I can go from A to G? No. So between any two vertices U and V, there will be exactly how many paths? 1. And here is the high-level proof. Suppose that you can go from U to V by one path. And then suppose that you can go to U to V by another path. So this is path 1, this is path 2. Guess what that looks like? That is a cycle, right? And we said that trees, by definition, are graphs with no cycles. So between any two vertices, there is exactly one path. Very highly structured here. All right? So trees are highly structured graphs. right? Now, why do we like that? Well, again, what are we trying to do? We're trying to create data structures. And if there's structure, you can exploit that structure. If you've got structure, then that means that you can make fast algorithms. You can make observations about other structures or structural characteristics of your data structure. And if you've got enough structure that you can exploit, then you can exploit that for fast data structures, order, log, and data structures if you really want. Right? Before we do that, though, we need orientation. All right? So let me go ahead and draw a very simple graph here. A to B, I don't know, tree that is, to C, D, E, and F. There we go. Now, don't read anything into the labels, A, B, C, D, E, F, G, whatever, right? The orientation that I'm going to do is imagine me grabbing this out of my paper here, say by D, and then holding it up and then shaking it and dangling it so that all of the other things, they're still rigid, everything's still connected, but everything falls due to the force of gravity. If I did that, then I would have D at the top, right? I'm holding D by my fingers at the top here, and everything else, falls. D is connected to B, it's also connected to E, and it's connected to F, right? Well, B has some things hanging off of it too. A and C is hanging off of A. So if I took it by B and then shook it, I could get something that looked like this. If I would select a different node here and shook it, I could get something that looked a bit different. Suppose I did it by E instead, right? And I took it out of the paper and I shook it. Well, D is hanging off of that. Off of D is hanging B and F. And off of B is hanging A and C, right? So it looks a little bit different when I write it like that, right? One of these versus the other, right? I'm just imposing an orientation here, right? This is the top of the tree, and this is the bottom of the tree, right? So in computer science, in CS, trees grow downward. Now, there are a couple of good reasons for this. The first reason is that Cayley, the mathematician who first defined trees and 150 years ago or something, just started drawing them like this, right? Why did he start drawing them like this? I don't know. At one point, when I was writing the book for this course, I went and got Cayley's original paper, and I read it, and he never justified why he wrote it like this. But it's clear that why would you care about this? Well, the nodes are going to be holding data. And how do you read data in English? You read it top to bottom, left to right. Like I wrote these. There was no accident that I wrote BEF. Why? Because that's alphabetic order. BF, right? I could have written it FB, but that would have looked weird because it's out of alphabetic order, right? We as humans like to naturally, instinctively impose ordering on things, right? So that we can understand it better, so that we can read it better. And that's what Cayley did. Cayley thought, well, these things are going to be holding data, or these things are going to be representing something. So we read in English top to bottom, left to right. So I'm going to orient my trees downward, right? And that's why our trees grow downward. There are lots of other situations in which trees grow downward, right? Think of a family tree. Your descendants are where in your family tree? Up there, right? Your ancestors, are up there, right? You're right here, and then your descendants, if you ever have any, are down here, right? So trees, family trees grow downward as well. And it's not too weird that CS trees grow downward. It's because we like to read our data left to right, top to bottom, okay? At the top, we have something called the root. You have the root, right? This is the root, and this is the root, right? For this tree and this tree respectively. Because, again, trees grow downward. So if you think of a tree, a natural tree, what's at the bottom of the tree? It's the root. That's the starting point. And then trees grow upward. Well, what do you have at the bottom? At the bottom, what do you have? For example, C and F here. Or C, E, and F over here. What happens when you get to the end of the tree? If you've got a natural tree and you go from the root all the way to the top, what's at the end? Leaves. All right? So, again, the orientation is completely arbitrary at this point. We're going to need more order and more structure on this in order to exploit it. But that's a pretty good start for now. Okay. Otherwise, in the middle, you can talk about now paths in the tree are called, you can call them branches, right? This one branches out into 3 others. This one branches out into one other, right? So we're also going to orient our trees left to right. Okay. So I'm going to go ahead and just draw an arbitrary node here, and I'm going to go ahead and excuse me. A, B, and C, okay? So we're going to establish more relationships here. I'll call this P up here, right? So if I'm given a node here, U, then if you think about it in terms of a family tree, where did you come from? You're U, right? Where did you come from? What terminology should I use here for this node here, P, now that we're oriented top to bottom? This is the parent. Parent of U, right? The node U. It's not the parent of A, B, or C, right? You can call, well, if I've got, here, let's define these. What should you call these things right here with respect to U? So if this is my parent, then my immediate descendants are called my children, right, of U, right? Now you can use other terminology. You can use, you can talk about cousins. You can talk about P is A's grandparent, if you want to talk about it like that. Or A is P's grandchild, if you want to talk about that. Great grandchildren, great grandparents, et cetera, et cetera. But we're only going to focus on the most immediate things here. Right? So given this terminology here, a leaf is a node with no children. That's that's a formal definition. How would you define the root then? The root, and it is unique, there's only one root, is the node with no, if that's the root, if I say that this is my tree now, all right, what can you observe? Well, here, let's look back at these. D and E. I called those the roots. Why? What unique property do those have? There's no parent, right? With no parent. Right? So a leaf is a node with no children, and the root is the node with no parent. Otherwise, sometimes if a node is neither a leaf nor a root, it's sometimes called an internal node, right? But we won't have cause to call it that, call attention to that too often. Okay. So those, again, you can go down with descendants, and you can go up with ancestors, because trees grow downward. Okay. A definition. We're going to put even more structure on our trees now. A tree. Here, let me go ahead and restart that. An oriented tree. Again, oriented downwards, such that no node has more than 2 children, is a binary tree. All right? It's perfectly fine to have a node with 2 children, right? In which case we call it the left child and the right child. Right? You can have a node with only 1 child, right? Say that it has a left child but no right child. You still orient it because it's oriented left to right, left child, right child. You can also have a node with the right child but no left child, right? So no right child, and this one has no left child. And then, of course, you can have a node such that there are no children, in which case it's a leaf, right? And then they're coming from somewhere else up in the tree, possibly, right? So this is why we call it binary tree, because it has at most two children, right? It could have one child or two children or zero children. Again, the word binary comes from the fact that it has at most two. It can have zero, it can have one or the other, or it can have two, right? Okay. So why are binary trees so nice? You can have ternary trees, quaternary trees. You can have arbitrary trees, B trees. They put a restriction on. You can up that instead of two. You can parameterize it and say that there are at most m children, right? Or they're between m children and m divided by 2 children or something like that. That's what's used in databases, B trees or B plus trees. What I want to do is I want to restrict my attention to the simplest form of this and look at binary trees, okay? And why that they're nice. But before we do that, let's get some more terminology here. What I'm going to do is I'm going to draw a binary tree here. Again, I don't care about the labels. We'll worry about that later. Oh man, I hope I gave myself some more enough room here. What I've done here is I have drawn a binary tree such that it's full, right? This is full. We need to talk about depth, right? So the depth of a node is the length of the unique path, a node, I'll call it U, from the root to U, right? So let's look at this one right here. What's the depth of this node right here? Remember that this is the root. So how can you get here? Well, starting from the root to this, you go 1, 2, right? That's the length of the path, the unique path from the root to this one. So what depth are all of these nodes at? At this level, it's going to be 2. What about this node right here? What's the depth of it? You just have to go 1 to get to it, right? What about these nodes down here? They're at depth what? 3. And if I had another level here, then it would be depth 4, depth 5, depth 6, etc. What about the root itself? What depth is it at? What is the length of the unique path from the root to the root? 0, because you're already there, right? So it makes sense to talk about those things, right? The depth of a tree, the depth of a tree itself is the largest depth of any node. So what's the depth of this tree? 3, right? That's its deepest level here. Only has a depth of 3, so the depth of the entire tree is at most 3. Now, there is also a concept of height of a tree. All right, turn it upside down, and now you can talk about the height of a tree. A height of a tree is actually defined with respect to a leaf node to that node. So, for example, the height of this is 1, 2, or it's just the opposite, basically. We're not going to be using that in this course, though. But you can talk about the height of a tree, but it's kind of awkward too because they're growing downward, right? All right. So my question here, if a tree is full, right? Like this tree is full, and of depth D, how many nodes does it have? Right? What about this particular example? How many nodes did I have? This tree has a depth of 3, right? In this case, the depth is 3. How many nodes do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 15. We usually use n to denote the number of nodes, right? Because that's going to be the size of our data structure, Just like order n, we're going to use n here. Right? But in general, what is it? Right? Let me draw another picture. I'll redraw the picture here. And let's go ahead and keep track of the depth and the number of nodes at this level. Right? And then, of course, you can draw it downwards. Right? So at depth 0, how many nodes are there? Just at that depth? 1. At depth 1, how many nodes do you have? 2. If I go one more depth, depth 2, how many nodes do I have there? 4. If I go one more, 1, 2, 3, 4, 5, 6, 7, 8. 3, now there are 8. Do you see a pattern emerging here? 1, 2, 4, 8, dot, dot, dot. If I'm at depth k, how many nodes do I have at that depth? 2 to the k. All right? So if I told you that the entire depth was d, then how many nodes are there at the last level if it's all full? And by full, I mean that every single one of these is here. Right? You don't have branches that are pruned off or anything. So at depth d, how many nodes are going to be at that depth? 2 to the d. Right? So sum these all up. This is my answer. How many nodes are there in this big giant tree of depth d? Right? Well, I'll do it on the same page here. All you need to do is a summation. What am I running? By the way, what is this right here? This is 2 to the 0, right? The depth. So if I go k running from 0 up to d, right? That's my variable here. And I take 2 to the k, and I sum them all up. What will I end up getting? This is a geometric progression, right? So what's the sum of powers of 2? Does anybody remember? Let's go back to this one example. 15. What relationship does that have to the powers of 2? 2 to the 4th minus 1, exactly. 16 minus 1, that gives me 15. So what's my answer over here? 2 to the d plus 1 minus 1, right? Sum of numbers. Now, this comes up all the time in computer science because of binary, right? If you've got 4 bits, then what's the maximum value that you can represent? Well, you start out with 0, 1, then 2, then 3, then 4. I'm not going to be able to do them all, but dot, dot, dot. If I've got 4 ones, what is that? What value is that in binary? 15, exactly what we just did before, right? And that's because that's the sum of the geometric progressions like this, right? So there's my answer. 2 to the d plus 1 minus 1. Now, why is that interesting? Because I'm going to flip it. If I've got a number of nodes and it's more or less full, then what's my depth? So I'm going to flip the question here. If a tree has n nodes and is almost full, what is its depth? Now, by almost, I mean that there could be some missing things right here. All right, you don't have to have a full tree every single time. But we'll go ahead and take the worst case scenario. Suppose that it is full, right? In other words, I've got that equation from before. 2 to the d plus 1 minus 1. If I'm given n, and this is n, what I'm asking for here is what's its depth? I need to solve for d, okay? So all I need to do is go n plus 1, take 1 onto the other side, is equal to 2 to the d plus 1. Right? Now, how do I get rid of this 2 so that I can play around with d? What do I do to the left side, or both sides? Log base 2 of n plus 1 is equal to d plus 1. Right? I just took the log of both sides to get rid of that 2. And again, remember, we don't care about bases. We won't write it at least, right? So if I take 1 onto the other side, then I get my answer is going to be d is equal to log, and I won't write the base here now anymore, plus 1 minus 1. Right? Now, what's the most significant term here? Take off lower order terms. Right? I've got log n plus 1. Go ahead and ignore that plus 1. Right? And I get that d is going to be what? Order log n. Right? That's why trees, binary trees, have the potential of for good operations. Right? So here's the takeaway from this motivation. If we can design a data structure such that insert, remove, and delete are all proportional to the depth, d, then they're all going to be order log n. Now, that's a tall order because, again, what caveat did we have to put up here? That it's almost full. You can have what are called degenerate trees. You've seen them, right? Let me go ahead and give you an example. A, B, C, D, E, dot, 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 down to Z. So there are 26 nodes here. On A has no left child. Likewise, B has no left child. Likewise, C has no left child, et cetera, et cetera, et cetera. What is this thing? It's a chain. What did we call those things? It's a linked list, right? So a linked list is kind of, you can look at a binary tree as kind of a generalization of a linked list. Instead of just having next, you have a left and a right child, right? And potentially not there, right? In this case, none of them are there. But if you have a restriction that you only have a right child or you only have a left child, or the orientation really doesn't matter. You could zigzag all the way down. If every node only has one child, right, then what do you have? Nothing more than a linked list. Okay? It's by branching out into one half of the tree and another half of the tree, that's where we get our power, right? That's where we get our structure to be able to exploit to get log n operations. Think about an array list, or an array, right? That's sorted 10, 20, 30, 40, 50, 60, 70, right? Go one more, right? How did we exploit this with binary search because it was sorted? What we could do is we could jump to the middle of the list and say, oh, it's either in that half or that half, right? We couldn't do that with a linked list because we can't jump to the middle of the list. But what we can do is we can start to build this thing into something that looks more like a binary tree. What if I did this instead? 40, I put that up as a root, and then I put in 20, and then I put in 10 and 30, and I put in 60, and what were the other two? 50 and 70, right? It looks kind of like this, right? All I did was split it, there's my root. If I look at this, I'm splitting it, and there's my root, And I built this little tree out of it, right? Now, I don't have the power of jumping to the middle in a linked list, nor do I have that even concept in a binary tree. But what's at the top now? What can I, by jumping to the top, what have I done? I've basically simulated jumping to the middle over here in an array, right? And I can look at this and say, oh, I'm searching for 5, right? And if you are highly structured like this, you could say, oh, well, if 5 exists, it either exists over here or over here. And if you're consistent about it and put things that are less over here and things that are greater over here, then what can you answer? I'm searching for 5. Where should it be? Over here. All right, there's your new tree. I'm searching for 5. Is it going to be the left or the right? If things in the left subtree are always less, right? Here's the concept. If I've got a key k, and everything over here is less than k, everything over here is greater than k, then where do I go next? If I'm searching for 5, go to the left. Oh, I'm still searching for 5, and I go to the left and I find what? It doesn't exist. At which point I'm done. How many comparisons did you have to make? 1, 2, 3 to see that it didn't exist. How many comparisons did you have to make over here to binary search to see that it doesn't exist? You jump to the middle, 1. Then you recurse over here. You jump to the middle, 2. And you see that you need to go to the left list. You jump to the middle, 3. You see that, oh, okay, you need to go to the left list. And then 4 to see that, or actually 3 to see, and then you don't do another comparison because you see that it's already empty, right? That your L and R have crossed, and so you stop the recursion, right? So basically, we took a note from the book of algorithms over here for binary search and said, gee, we can't do that with a linked list, but what can we do? Well, we can start to bend it into 2 sublists, in which case it gives us a tree that looks like this instead. And now we don't need random access. We don't need to jump to the middle as long as it's highly structured like this. All right? This is called a binary search tree. All right? Make sure that I'm good on time. All right, good. And that's what we're going to ultimately work towards. But before we get there, we need some other algorithms on trees. Okay? Let me see. Yep. So we need to start working with trees to get a little bit more practice here. Right? So given a binary tree, and now it's not binary search tree yet, but you can run the same algorithms on it. Given a binary tree, you want to do, say, a linear search. Perform a linear search to find an element, or just to enumerate, and by enumerate I mean list, all its nodes. Okay? Now, if this were a linked list, it'd be pretty straightforward, right? If I had 10 going to 20, going to 30, it's pretty clear where to start. This is the head. And then you'd go to the next. Like, if I start at the head, is there anywhere else to go? How many choices do I have? Where can I go next? Just over here. My choices are restricted for a linked list. Go to the next, go to the next, go to the next, right? But if it's a binary tree, say A, and then B, C, D, E, and I'll put a right child, F, but no left child, G, and say H and I. Okay? Now, as a human looking at this, you can go, oh, okay, like we'd like to read top to bottom, left to right, A, B, C, D, E, F, G, H, I, right? And that's how I wrote it, right? Naturally, right? But if you're a computer, if you're a dumb computer, and you only have access to the root element, how do you list all these things out to make sure that you didn't miss anything? Okay? So, in other words, using only local information here. How do you enumerate all these things? Well, I can start at the root. Okay, well, A is there. But now I don't have my restriction of choices over here. Just go to the next, go to the next, go to the next. I've got 2 choices now. Do you go to B first, or do you go to C first? And if you choose one or the other, how do you know that once you're done, you still need to explore that other tree over there? Right? Take a vote. Do you want to go to B first or C first? B? Okay. Go over there, do whatever you're going to do over here. How do you know, oh, once I'm done over here, how do I know to go back over to C here and do C, F, H, J, H, I, blah, 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 right? Once you've made your choice to go to B, now you have 2 more choices. Do you go to D or E? Well, we went to the left child on the first one, so let's be consistent and go to the left child on the second one. D, right? I went A, B, D. I basically have a linked list here, right? If you look at it like this. I went A to B to D. How do I make sure, but now I'm at a dead end, right? How do I make sure to go back? Where do you go back? Okay, you could go up. You could just go back to the immediate predecessor here, and then there's a right subtree, so I need to take care of that. Right. So what we kind of just put together is called a preorder traversal. So definition: a preorder traversal of a binary tree enumerates nodes in a root, left, right order, and I will use the R word here, recursively. All right, and we'll look at the recursive version of this, but then we'll get rid of the recursion and use a smart data structure because it's a lot better. Right? What I'm going to do is I'm going to copy this over because it is an interesting tree, and we're going to go with a preorder traversal of it. A to B to C, D and E hanging off of B. So both, all the children so far. But then C does not have a right child. And then we've got F over here. D has no children, so it's a leaf. E has a left child, so G is a leaf. And then we have an H and an I hanging off of F. Okay? Let's do a preorder traversal of this. A preorder traversal always starts at, so you start at the root. And then you enumerate things in a root, then left, then right manner. All right? So what I'm going to do is I'm going to start at the root, and I'll do my enumeration down here. What's the first thing that you see? Is you see A. Right? Now what we're going to do is we're going to then explore the left subtree. After we're completely done with that left subtree, we're going to come back and explore the right subtree because we're going root, then left, then right. When I look at this subtree here, B is not the root in the original tree, but if I cut it off and only look at this branch, right, then B is my new root. Right? And so I start over again recursively. I enumerate the root, then the left, then the right. So I will enumerate B next. And then I go to its left subtree. Again, cover everything up here. And I go with a root, left, right. Well, that's D. Right? In fact, let me go ahead and cover all this up. Now, what's the left child of D? Nothing. I'm done. What's the right child of D? Nothing. I'm done. So I go back to where I came from, B. Now, I've already, I did root. Let me cover this up. I did the root. I already did the left and did everything over here. Now I need to do the right. So now this is my new tree, my new subtree. I go root, left, right. So what's next? What's my new root? E. Right? Then I do left, then I do right. Well, left, there's my new tree. Right? What's the root of that tree? G. Is there a left? Nope. Is there a right? Nope. So move on. Come back up here to E. I'm not done with E because I did E and then I did its left subtree. Now I need to do its right subtree, but guess what? It doesn't exist. So I come back up. I did B, I did its left subtree, I did its right subtree, so I come back up. Right? It's recursion down, it's returning from the recursion on the way up. So I did A and I did its entire left subtree. Right? B, D, E, and G were all enumerated. And now I need to go to its right subtree and start the process again. Now my new root is C. So I do C, and then I do its left subtree, but guess what? It's empty. So I've done C, its left subtree, and now I go to its right subtree. And given just a three-node tree, hopefully you can just bang that out. What's the next order? Root, left, right, so F, H, and I. Now, is this in alphabetical order right here? Nope. Even though I drew it in alphabetical order, top to bottom, left to right, my preorder traversal here came out with a different ordering. Okay? So let's go ahead and think about how we can actually implement this now. But before we do that, we're going to have to talk about how to implement an actual tree. Right? So how do you represent a tree, say in Java, or just pseudocode here? Right? So pseudocode binary tree. Right? Let's first think about a node. What else? So if this were Java, I would create a node class, just like I did with linked lists. I would have a node and then parameterize it along T. Well, nodes hold, the purpose of nodes is to hold data, right? So I would have, like, say, the item, right? This is the data item or label, right? What else would you have in a node? Take B. What do you have in B? You have B, the item itself or the label. But what else do you have? You need references, right? One reference that you need is to the left child, to the right child. And what other reference would be nice to have? The parent, right? If you only look at the local information here, then you have a left child, maybe it's null, maybe it's missing, nil, phi, whatever you want. You have a right child, and hopefully you have a parent so that you can go back up the tree if you really want to. So you would have a node called left child. You would have a node called right child. And you would have a node called parent. Now, implementing it with a parent is not absolutely necessary, but it's really convenient if you do it this way. So that's my node class. And so if I'm going to write some pseudocode, if I give it a node u, I'm going to use the convention that I can use the dot operator to access its left child, that I can access its parent, and I can access its right child. Or I can access its item. Right? That's the node class. What would your binary tree class look like? Now, would it make sense to have a list, an array list of all my nodes? I'm back at square one, right? And now I've got a list data structure and not a tree data structure, right? So, like a linked list, you don't keep track of all the nodes, you only keep track of one. What node should I keep track of in a binary tree? Where do you start everything? The root. Optionally, you can keep track of the size, right? So that you don't have to, well, how many nodes are in this tree? 5? You have to go through and count them all in order to answer that question. No, you can insert something and increment the size. If you remove something, you decrement the size, just like we did with linked lists, so that you wouldn't have to traverse the entire list just to find out how many things are actually in there. Okay? All right, that's our implementation of a binary search tree. And again, if it were Java, it would just be node, you parameterize it T, give this a T, and then node T, node T, node T, et cetera, et cetera. Make them all private, create a constructor, create a bunch of getters and setters, et cetera, et cetera. If you want all the details, I think I do those in the videos. Okay? But now that we've understand how to implement a binary tree, how do we implement that preorder traversal? Right? So preorder traversal. Right? We're not going to be given a tree. Instead, suppose that we're given a node u, right? Node u, right? So again, if you want to do proper pseudocode here, input is a tree node u, and our output will be a preorder enumeration from u, right? So initially, the root is going to be given to this recursive function here, Okay? So what's the first thing that we should do? What's the first thing we did over here? If I gave you A, what's the first thing you did? Right here. We output it, right? So given U, we'll go ahead and output U. Right? That's the first thing that we did. Then what's the next thing we did? Remember, it's root, left, right. So what's its left child? B. And I would recurse on that. So preorder traversal of U's left child. All right? What do we do next? This is going to go down to the left subtree, and it's going to take care of everything for me, right? I recurse on B, then I recurse on D, then I recurse. The return on that recurse comes right back to this this recursive call, and I'm back to having U here. Right? What do I do next? I went with the root, the left subtree, then what? I go to the right. U dot right child. There we go. That's it. Right? Now, technically, this is pseudocode, so if U doesn't exist, it's nil, it's phi, whatever, then you don't output it. So you could put an if condition here that if U is null, then you don't do anything and you simply return. Otherwise, you do a preorder traversal on its left subtree, preorder traversal on its right subtree. And if this were Java and U were null, then this, of course, would be a null pointer exception. Right? You need to take care of that. But this is just pseudocode, so I'm not going to worry about those details. Right? Extremely simple. Right? This is the one time that I would tend to somewhat agree with somebody who really likes recursion. Like, wow, that's so simple, right? All you need is output, call function, and you're done, right? And if you wanted to do a recursive version of this, this is perfectly fine, right? But I would still disagree and say, yeah, it looks nice, but it's that's an aesthetic. That's a subjective point of view. Three lines of code, of pseudocode at least. One person's simple code is another person's complicated code, and one person's complicated code is another person's simple code. So I would say that by that standard, this is merely subjective, right? Yeah, it's beautiful, sure, right? Go ahead. But what I would consider beauty and elegance is a smart data structure instead, right? Now remember the idea here. You start at A, and then you need to go and do, its left subtree, whatever. But you also need to keep in mind, wait, after I'm done with this left subtree, I need to come back and explore the right subtree, right? So how do I keep track of that, right? Here's the idea. If I'm at U, I will go ahead and explore the left subtree, but I need to remember, after you're done with this, explore the right subtree. Keep track of this. Don't lose that, right? How can I remember that I still need to go down that way, right? Think of it this way. If I started at A, then went to B, then went to D, right? A, B, D, right? And this is not exactly, but it gives you the hint of what kind of data structure we're going to look at here. What have I done? I've kept track of breadcrumbs. I went from A to B to D. Well, where did you come from? I'm only at D. That's all I see. But I can see over here, oh, I'm at D. I came from B to get here. And from B, I came to A to get here. What kind of a data structure am I keeping track of my breadcrumbs with? A stack. Why? Stack is, what was it called again? LIFO order, last in, first out. The last one to be put in was where you came from. You came from A to B to D. Right? If you start popping these off, then you are recursing back up the tree, and it takes you back to where you came from. Now, that's not exactly the idea, but it's very, very similar, and it gives you the basic understanding of how we're going to use this stack. I'm going to go ahead and simulate the algorithm, and then we are going to go ahead and design the algorithm probably next time. Right? Go over to F, H, and I. There we go. Right. And here's my I'm going to do it in pencil because I'm going to be erasing stuff. Right? Hopefully you can still see it. Yep, you can. All right. What I'm going to do is I'm going to start at A. I'm going to push it. Right? That's where I am right now. And then I'm going to pop it, right, immediately. So X is equal to A. Or instead of calling this X, let's call it what it is. Current node. Right? I'm at A. I'm going to pop it, and it's gone now. I'll bring a more erasable pencil next time. Right? Now I need to keep track of. Okay, I'm going to go to B next. So I'm going to output. Here's my enumeration. Right? So I'm going to output the current node, but then I need to look at its children, B and C, and I need to put these in the stack such that I'm going to go ahead and go down B this direction first, and then when everything is done, I will come back and do this over here. So which order should I push these in? Should I go with B and then C? The last one in is the first one out. So on the next iteration of this algorithm, when I pop this off, which direction will I be going? To C. That's the wrong direction. I need to go to B next. So I will push. In which order should I push these then? The left child or the right child first? I need to make it look like this, C and then B. So which one should I push first? Push the left child, and then push the right child. All right? Now, I've got B and C here, and there's my current node. Next iteration. I pop, and this becomes B, and now B is off the stack. Right? C is still in there, keeping my breadcrumbs that when I'm done over here, I need to come back and handle this subtree over here. All right? Do it again. I will output B, output current node. Right? Push the left child, E, then push the right child, or wait, yeah. I've screwed up my left and right, I'm sorry. Left and right. So what order should I have done it in? I should push right. I didn't screw up the algorithm. I screwed up my left and right hand. There we go. Right and left. There we go. And so I go C and then E. All right. That's why I was getting some looks out there. So then E, then D. There we go. So push the right child, push the left child of the current node, which is B. Right? And then go on again and do this again. This becomes D, and we output it. Output the current node. Push the right child. Well, guess what's there? Nothing. Push the left child. What's there? Nothing. Right? So I pop this, sorry. And so I keep track that, oh, now what's next? E. E gets popped off. That's my current node now. And then I output it, E, and I look at its right child, which doesn't exist. So push its left child, G. Right? Next iteration, G gets popped. And I output it, but I don't push a right child or a left child because they don't exist. So on the next iteration, I'm done with the left subtree here. What's still in the bottom of the stack here? C. So that gets popped. And I start everything over here again on this subtree. I output C. I push its right child, F. I push its left child, which doesn't exist. Do it one more time, or a couple more times. F gets popped. Right? And I push its right child, I, and its left child, H. Right? And outputting F. Right? And then I pop H, output it. There is no right child, there is no left child, so nothing else gets pushed. And at the very end, I pop I, I get output. There is no right child, there is no left child, so there's nothing to push. And at that point, I'm done. I have the exact same